So electric dipole means we are having two equal charges in opposite direction. Suppose like this. This is plus Q. This is minus Q, which are separated by a distance d. It forms an electric dipole. Then, if you want to calculate at a point P the electric field intensity, the distance is R. R is very greater than D. R is very greater than D. So this forms an electric dipole. So what is the field intensity? Electric field intensity. What is the electric field intensity at P? At P is equal to how much? We want to calculate because of this electric dipole. Here I am giving the expression directly. I am not going for the derivation of this. The same procedure we can apply. What we discussed for previous problem. If you calculate, you will get E is equal to Q into D by 4 pi epsilon naught R cube into 2 cos theta A R bar plus sin theta A theta bar. So this is the electric field intensity due to a dipole. Because here I am assuming spherical distribution, because this is plus Q, this is minus Q. The field intensity is like this, starting from positive to ending with a negative field, a negative charge. So the field distribution is like this. So it is nothing but in the spherical distribution. That's why here we can analyze this problem with the help of a spherical distribution. So this is the field distribution of a electric dipole. So we can assume spherical distribution. Here the important point is not the expression at all. The electric field intensity is inversely proportional to 1 by R cube. Electric field intensity is inversely proportional to 1 by R cube. This is for a dipole. Dipole means two charges. Suppose if you consider point charge. For a point charge, E proportional to 1 by R square. E proportional to 1 by R square. Whereas for an electric dipole, electric field intensity is inversely proportional to 1 by R cube. 1 by R cube. So this is an important point we have to note here. That is, the electric field intensity of a dipole varies as 1 by R cube, in contrast to that of a point charge, where in point charge the field intensity varies as 1 by R square. 1 by R square. So this is this diagram is E field intensity. E field intensity of a electric dipole. That is, therefore, the electric field intensity of a dipole varies as 1 by R cube. So which is very important statement. Next concept is electric fields due to continuous charge distribution. Electric fields due to continuous charge distribution. So till now we have only considered forces and electric fields due to point charges. So the meaning of point charges which occupies very small physical space. So now we will discuss some charge distribution, continuous charge distributions along a line, on a surface, or in a volume. And we will calculate what is the electric field intensity due to this charge distributions. So this is point charge which occupies very less space in less volume in space. So till now we consider forces and electric fields due to this point charge. Now we can define some charge distribution along a line. Suppose if I say this is a line. So suppose if the charge distributed like this. Here I am considering positive charge. So this is called line charge. This is called line charge. So what is the electric field intensity due to this line charge? We have to calculate. So this line charge is indicated with line charge density. Point charge indicated with Q. Similarly, line charge is indicated with line charge density. Line charge density, that is Royal Coulomb per meter. Royal is given by Q by L, where L is the length of the line. Similarly, surface charge. Suppose closed line. This is a closed line. Closed line is nothing but a surface, open surface. Suppose if a charge is distributed along the surface, then what is the electric field intensity due to this sheet? This is called surface charge. Surface charge is indicated with surface charge density. Surface charge density given by a symbol rho s. Surface charge density. Unit is Coulomb per meter square. Rho s is equal to Q by A, where A is area of the sheet. Q by A, area of the sheet. Similarly, volume charge, that is closed surface. This is a closed surface. So some charge exists in the volume. Volume is nothing but closed surface. So this is called volume charge. So we have to calculate electric field intensity due to this volume charge. So volume charge is indicated by volume charge density. Volume charge density, rho v. Unit is Coulomb per meter cube. Rho v is equal to Q by V, where V is volume. So these are other charge distributions, continuous charge distributions. We have to calculate the electric field intensity due to these charges. So first I am considering line charge. So what is the electric field intensity due to E field due to line charge? We have to calculate. So for that what I am doing, I am keeping this is X, Y, Z coordinate system. I am keeping a line charge with line charge density rho L on along Z axis. So this is length AB. This is length AB. Then we have to calculate at a far point P what is the electric field intensity due to this line charge. So for the analysis I am considering a small length DL. Small length DL. So this is the distance from this. So like this we can complete the graph. So we have to derive electric field intensity. So here I am assuming a cylindrical distribution because a closed line, a line is in the form of a cylinder like this, but radius is very low. So I am assuming here cylindrical distribution. So here line charge density is rho L. Therefore, the small charge dq is given by rho L into dl. dq is equal to rho L dl. That is, the small charge element is rho L dl. So total charge q is nothing but integration rho L dl from A to B. If you integrate from A to B rho L dl, you will get a total charge. Then I have to calculate electric field intensity due to this. Suppose the distance is r. I know that E is equal to, so I am keeping a unit charge here, q by 4 pi epsilon r square ar bar. But here q is nothing but rho L dl by 4 pi epsilon naught r square ar bar. So that is equal to 1 by 4 pi epsilon naught integration rho L dl into 1 by r square ar bar. Now we have to calculate r. So this point is x is 0, y is 0, z is some z dash from origin 0 0 0 0 some suppose z dash. So this point is x y z because this is any point, it may be x y z, general point. Therefore r is equal to x y z minus 0 0 z dash, that is given by x ax cap plus y ay cap plus z minus z dash az. So modulus of r is equal to square root of x square plus y square plus z minus z dash whole square, that is equal to square root of rho square, x square plus y square, I can keep it as rho square plus z minus z dash whole square. So this is also equal to rho a rho plus z minus z dash az. I can simplify like this because here I am assuming cylindrical distribution for easy analysis. So substitute these values in the integration, and if you simplify, you will get the answer. So this is a general procedure. To simplify the to calculate electric field intensity. But for our examination point of view, we don't need these derivations. Generally, this is a procedure. We don't need these derivations. We need some shortcut formulas how to calculate electric field directly. So we will discuss that thing now. So now we will consider a special case. What is that special case is for an infinite line charge. If it is a finite line charge, we have to follow the conventional procedure. But generally some special cases for an infinite line charge means point A is at 0 0 minus infinity, point B is at 0 0 infinity. If you substitute this value, if you calculate for infinite line charge, the electric field intensity is given by rho L by 2 pi epsilon naught rho a rho cap. So this is the electric field intensity due to a infinite line charge. This formula is very, very important. The electric field intensity due to a infinite line charge is given by rho L by 2 pi epsilon naught rho a rho. Generally, this is valid for, this is a general formula. So here we can define rho L is, we know, rho L is line charge density. We know it. Rho is here, rho is perpendicular distance. Rho is perpendicular distance from from the line to point of interest. From the line to point of interest. Suppose this is the line. If you want to calculate field here, so this is from line to point, perpendicular distance from line to point. This is rho. This is rho. So this is the meaning of rho. Here rho is unit vector along rho. Unit vector along rho. So we can easily calculate the electric field intensity. The electric field intensity by using this formula for a infinite line charge. Now we will see a surface charge. So over here I am consider a infinite sheet. Consider a infinite sheet with surface charge density. The surface charge density rho s. Surface charge density rho s. So like this. This is x, y, z. I am considering in xy plane I am considering a sheet like this. So this is infinite in length. This is infinite in length. This is the sheet. This is the sheet having rho s charge density. So the electric field E due to this rho s at any point is given by rho s by 2 epsilon naught a n cap. The electric field intensity due to this surface charge, infinite surface charge density is given by rho s by 2 epsilon naught a n cap, where a n bar is a unit vector normal to the sheet. Where a n bar is a unit vector normal to the sheet. Where a n bar is a normal vector to the sheet. That is, suppose if you keep at z is equal to 0, the sheet is at z is equal to 0. So like this, at z is equal to 0 I kept the infinite sheet. So the only possibility is above the sheet, that is for z greater than 0 or less than 0, z less than 0, that is below the sheet, I can calculate electric field intensity. Suppose if z greater than 0, that is if you are calculating electric field intensity above the sheet, you have to consider the normal vector in positive direction, that is a n bar is equal to az. Suppose if you are calculating electric field intensity below the sheet, that is for z less than 0 region, the normal vector is minus az. Because that's why here the general definition is a n bar is a unit vector normal to the sheet. So depending upon the point where you are calculating electric field intensity, you have to consider a n according to the point. So this is the best example. Suppose z greater than 0, a n is equal to az, z less than 0, a n is equal to minus az. One more interesting point of this is, suppose if you observe this electric field intensity, it is given by rho s by 2 epsilon naught. Rho s is surface charge density. We know rho s is surface charge density. 2 epsilon naught. 2 is constant. Epsilon naught also we know. Epsilon naught is free space permittivity. Free space permittivity. So this is also a constant value. So the electric field is independent of the distance between the sheet and the point of observation. So this is a very, very important point. The electric field The electric field is, first one is the electric field is normal to the sheet. The electric field is normal to the sheet, always normal to the sheet, and is independent of distance between the sheet and the point of observation, So this is one of the important point of this sheet surface charge distribution. Of course, here I am not deriving how we got this. You can refer any standard textbooks. The derivations are very lengthy, which will consume more time. That's why directly I am giving the formula here. So E is equal to rho s by 2 epsilon naught A n cap. So you have to keep in mind this formula to solve the problems. So this is the electric field intensity due to a surface charge.